Today we are going to learn about mastering PyTorch checkpointing techniques. You will gain skills in implementing, managing, and troubleshooting model checkpointing to optimize your PyTorch projects efficiently. Welcome to our video on mastering PyTorch checkpointing techniques. In this session, we will explore the crucial role of checkpointing in training deep learning models using PyTorch. Checkpointing refers to the process of saving a model's state during training. It's particularly useful in long training sessions, where interruptions can occur due to hardware issues or scheduled maintenance. By regularly saving model states, you can recover from such interruptions without losing significant progress. Moreover, checkpointing allows you to experiment with different model states, enabling you to fine-tune your models for better performance. Throughout this video, we will delve into various checkpointing techniques, providing you with the knowledge to implement and manage checkpoints effectively in your PyTorch projects. Checkpointing offers several significant benefits in training deep learning models. Firstly, it saves time and computational resources. By periodically saving the model state, you can avoid retraining from scratch in the event of an unexpected interruption. This not only speeds up the overall training process but also optimizes the use of computational resources. Secondly, checkpointing ensures continuity in training. Should a training session be halted, you can resume from the last saved checkpoint, preserving the progress made up to that point. This continuity is crucial in environments where training can be interrupted by server downtimes or resource reallocation. Additionally, checkpointing facilitates model experimentation. By maintaining different checkpoints at various stages of training, you can experiment with different configurations and hyperparameters without starting over. This capability enhances the robustness of your training process and can lead to improved model performance. In essence, checkpointing is an indispensable practice for anyone serious about training effective deep learning models in PyTorch.
Now, let's dive into a practical guide on how to save checkpoints effectively using PyTorch. The first step is defining a checkpointing strategy. Determine the intervals at which you want to save the model's state. This could be based on epochs, iterations, or time intervals depending on your specific needs. Next, leverage PyTorch's built-in functions for saving checkpoints. The torch.save function is your primary tool here, allowing you to serialize the model's state dictionary to disk. When saving a checkpoint, it's crucial to include both the model's state and the optimizer's state. This ensures that when you resume training, the optimizer can continue from where it left off, maintaining the learning rate schedules and other parameters. Additionally, choose appropriate save intervals that balance between too frequent saves, which can be resource-intensive, and too sparse saves, which risk losing significant progress. Lastly, ensure version compatibility. PyTorch updates can occasionally affect model serialization, so it's good practice to document the PyTorch version used for training in your checkpoints. By following these steps, you can maintain an efficient and reliable checkpointing system in your PyTorch projects.
Restoring models from checkpoints is a critical aspect of using checkpointing effectively. The process begins by loading the saved state dictionary into the model. PyTorch's torch.load function is used to load the checkpoint file, followed by the load_state_dict method to update the model's parameters with the saved state. It's equally important to restore the optimizer's state to resume training seamlessly. The optimizer's state dictionary is included in the checkpoint and should be loaded similarly to the model's state. This step ensures that the optimizer continues from its last state, preserving the learning rate and other settings. When restoring from checkpoints, be mindful of potential version mismatches. If the checkpoint was created using a different PyTorch version, it might result in compatibility issues. Always document the version used during checkpoint creation to prevent such problems. After loading the checkpoint, verify the model's integrity by running a few validation steps to ensure everything is functioning as expected. By mastering these restoration techniques, you can efficiently resume training and make the most of your saved checkpoints.
Effective management of checkpoint versions and storage is vital for maintaining a streamlined workflow. Start by organizing your checkpoint files logically. Use descriptive file names that include the model name, epoch number, and date. This practice aids in quickly identifying and accessing specific checkpoints when needed. Implement a versioning system to track changes and improvements in your models over time. This can involve maintaining a separate directory for each training session or appending version numbers to your checkpoint file names. Monitoring storage requirements is crucial to avoid running out of space, especially when dealing with large models or frequent checkpointing intervals. Consider automating the cleanup of old checkpoints to free up space and keep only the most relevant ones. Additionally, use efficient file formats like .pt or .pth to save checkpoints, as these formats are optimized for PyTorch models. By managing checkpoint versions and storage efficiently, you can maintain an organized and scalable checkpointing system within your projects. Automating the checkpointing process can significantly enhance training efficiency and reduce manual intervention. One effective method is integrating callbacks within your training loop. PyTorch Lightning, a popular framework built on top of PyTorch, offers a convenient way to implement checkpointing callbacks. With callbacks, you can automate checkpoint saves based on predefined criteria such as improvements in validation accuracy or loss reduction. This automation frees you from manually tracking model performance and deciding when to save checkpoints. PyTorch Lightning's model checkpoint callback is particularly useful, allowing you to specify criteria like the metric to monitor, the mode, min or max, and the frequency of checkpoint saves. Additionally, you can customize the save criteria to suit your specific training goals. By automating checkpointing, you streamline the training process, focus more on model development, and ensure important model states are consistently saved without manual oversight. Deciding between cloud and local storage for checkpoints depends on your project's needs and resources. Cloud storage offers several advantages, such as scalability, ease of access from multiple locations, and off-site backup. However, it comes with storage costs and potential security considerations. Evaluate these factors to determine if cloud storage aligns with your requirements. Implement secure cloud storage practices, such as encrypting checkpoint files before uploading and using access controls to protect sensitive data. On the other hand, local storage provides quicker access and avoids cloud-related costs but requires adequate disk space and backup solutions to prevent data loss. Optimize local storage usage by regularly archiving old checkpoints to external drives or secondary storage devices. Consider your data accessibility needs when choosing between cloud and local storage. If your team collaborates remotely or requires frequent checkpoint access from different locations, cloud storage may be more suitable. By balancing these considerations, you can select the most appropriate storage solution for your PyTorch checkpoints.
Even with careful planning, checkpointing issues can arise during training. Common problems include version incompatibility, corrupted checkpoint files, and optimizer state issues. To resolve version incompatibility, always document the PyTorch version used for creating checkpoints and test compatibility when upgrading PyTorch. For corrupted checkpoint files, implement regular validation checks to ensure file integrity after each save. If a file is found to be corrupted, consider reverting to the previous checkpoint or using backup copies. Optimizer state issues can occur if the optimizer's state dictionary is not correctly restored. Double-check the restoration process and verify that the optimizer's state dictionary matches the model state. Additionally, ensure consistent checkpoint saves by verifying the criteria and logic used in the saving process. By proactively identifying and addressing these common issues, you can maintain a robust and reliable checkpointing system, reducing training disruptions and enhancing model performance. In conclusion, mastering PyTorch checkpointing techniques is essential for efficient and effective model training. Throughout this video, we've explored the benefits of checkpointing, from saving time and resources to facilitating model experimentation and ensuring training continuity. We've covered practical steps for saving and restoring checkpoints, managing versions and storage, using callbacks for automation, and troubleshooting common issues. By implementing these techniques and best practices, you can optimize your PyTorch projects, ensuring robust model development and training efficiency. Remember, continuous learning and adaptation are key in the ever-evolving field of deep learning. Thank you for joining us on this journey to mastering PyTorch checkpointing techniques.